All right, folks, what we're going to do is we're going to graph another rational function here. I've got this 4x minus 20 over x squared minus 2x minus 15. We're going to identify all the qualities that we can about this rational function, and then we're going to graph them. We're going to graph them a little differently. This time, you can see I have no coordinate plane here, but we can still graph a rational function even without a coordinate plane if we just draw a y-axis and an x-axis, so x and y, and then what we'll do is we will label all of the points and label all of the asymptotes so that we can know where they are, but not necessarily count them on a grid. Okay? All right, so here we've got this, what's the first thing that we're going to do with any function, any rational function, so that we can find all these qualities? We are going to factor the numerator and factor the denominator. So when we factor the numerator, see there's a common factor in there of 4, so we can divide out a 4, and we'll have 4 times x minus 5 over, we got to factor this x squared minus 2x minus 15. Two numbers that multiply to negative 15 but add up to negative 2 are negative 5 and positive 3. So we're going to put x minus 5 times x plus 3. And now with this in factored form, it's easier to identify all of these qualities. Now, the first thing we can do is we can identify that we can see right away that there is a hole because there's an x minus 5 in the numerator and an x minus 5 in the denominator. So we can cross that out. And we know that there is a hole at x equals 5. So over here we're going to say there's a hole at x equals 5. Now we want to identify the actual coordinates of this hole because we just learned how to do that. And the way we're going to actually identify the coordinates of the hole is we're going to plug the x value for the hole into what is left over in the function. And we have 4 over x plus 3. So we're going to have 4 over x is 5, so that's 5 plus 3, 5 plus 3. So that's 4 over 8, and 4 over 8 reduces to 1/2. Okay, so this hole is at 5 and 1/2. So x coordinate 5, y coordinate 1/2. And what we can do here is we can come over here and we can sort of count out or just put a line over here and say, you know what, that's 5. Okay, when you don't actually have a grid, you can just put a line approximately where that value should be, and we'll call that 5. And then what we'll do is we'll just put a dot here and we'll call that 5 and 1/2. That's a little bit of a large circle. Let's make it a little bit smaller. There's a hole, and we're going to put parentheses. And we're going to say that this is 5 comma 1/2. 5 comma 1/2. That's that point right there. That's the hole. All right, so we've got the hole. Let's identify the y-intercept now. If we were to plug 0 into x here, we would have 4 over, what's 0 plus 3, right? 0 plus 3 is 3, so we have 4 over 3, that's 4/3, right? Which is approximately 1 and 1/3, but we typically deal in, don't deal in mixed numbers, we typically deal in improper fractions. So we're going to say y-intercept is at 0 and 4/3. Now that is approximately, if this, see that dot right there, is at approximately, if that's 1/2, then 1 would probably be here, and 1 1/3 would be a little bit above that. So let's just put a dot there. See how without having a coordinate plane, we can still roughly sketch something, but we just have to label, and we're going to say that that point is 0 and 4/3. That's that point right there. All right, so we've got our y-intercept. Now let's identify the X-Intercept or X-Intercepts. And the way we identify the X-Intercepts is we set the numerator equal to 0. Now, after crossing out the x minus 5, what's left in the numerator is 4. So if we say 4 equals 0, well, that doesn't make sense. There's no variable here. 4 does not equal 0. 4 cannot equal 0. And therefore, the conclusion is there is no X-intercept. If the numerator cannot equal 0, then we say That there aren't any. There are none. How many X-intercepts are there? None. There aren't any. So we're not even going to plot an X-intercept here. And you'll see why in just a minute. There's something interesting going on at the y-axis. So let's identify the vertical asymptote. In order to identify the vertical asymptote, we set the denominator equal to 0. And after crossing out the whole, we have x plus 3 in the denominator. And if we set that equal to 0, we're going to subtract 3 from both sides, and we get x is equal to negative 3. And so we have a vertical asymptote at x equals negative 3. So we're going to go over here to approximately where negative 3 would be. I'm just kind of guessing it's obviously on the negative side of the x-axis, and we don't want to quite go as far as 5, so let's maybe go right here, and we'll call that x equals negative 3. And there we're going to draw a vertical line. Now you can use a ruler. I'm going to use a level. I know that's a little geeky, but I'm going to use a level to make sure that it's as vertical as I can possibly get it. That's about vertical right there. We've got a vertical asymptote there at negative 3. Okay? And then now we need the horizontal asymptote. For the horizontal asymptote, we can look back at the original function. We don't have to worry about the crossed out. We can look at the revised function here, 4 over x plus 3, and it'll still work. In fact, let's go ahead and do that. Our revised function here, after crossing out the whole, is 4 over x plus 3. Well, we want to compare the x power in the numerator versus the x power in the denominator, right? Well, what is the x power in the numerator? There's no x in the numerator. That means the x power in the numerator is 0. The x power in the denominator is 1. And 1 is larger than 0. That means that the denominator has a larger x power than the numerator. The denominator has a larger x power than the numerator. And when that happens, the horizontal asymptote is at y equals 0 every single time. So we're going to say that there's a horizontal asymptote at y equals 0, which is the x-axis. The x-axis is the same thing as y equals 0. And the reason we know that is because, look, up here, y equals 1. Down here, y equals negative 1. Well, that means here, what's between negative and positive? 0 is between negative and positive, so that means y is equal to 0 here. So here, we're going to draw a dashed line. Okay, and we have a horizontal asymptote on the x-axis at y equals 0. Now, last thing we got to look at is slant asymptote. Well, we've already learned if a function has a horizontal asymptote, it does not have a slant asymptote, and therefore there is no slant asymptote. In order to have a slant asymptote, the numerator power would need to be 1 larger than the denominator power. The denominator power here is 2, so this would have to be a third power numerator, and it is not. Therefore, there is no slant asymptote. And now that we have all that information, we can now sketch our graph. Okay? Now we know that this graph is going to go through this point and through this hole. Okay? And we also know, if you look at it, this point is higher than this point. We have a horizontal asymptote here and then a vertical asymptote here, which means that the graph is going to curve against the vertical asymptote. It's going to kind of go vertical, and then it's going to go through this point, and then it's going to go through the hole, but I'm going to hit the hole and then pick up on the other side, and then it has to bend against the horizontal asymptote. And so there is one part of it. Now, we don't know what's going on the left side of this vertical asymptote. So what we're going to do is we're going to plug in a test point to find out whether the left side is on the top or on the bottom. And we have we want to be on the left side of negative 3, and on the left side of negative 3, probably the easiest thing to plug in would be negative 4. So if I plug negative 4 into this right here, I would have 4 over negative 4 plus 3. 4 over negative 4 plus 3. Negative 4 plus 3 is negative 1. So that's 4 over negative 1, and 4 divided by negative 1 is negative 4. So this function will pass through the point negative 4 and negative 4. And so I'm going to put a dot here, and we can plot it, but we don't really have to plot it. We just want to approximately know. We want to know whether the curve is above the asymptote, the horizontal asymptote, or below the horizontal asymptote. We know that it's below, and so we're just going to kind of sketch this curve and bend it against the asymptotes. And there, we're done. This is the graph of 4x minus 20 over x squared minus 2x minus 15. Just a rough sketch. And there you go.